Hello, we are the L3Harris Clinic Group, and we are proud to show you our project, which we call DDOM, which is an acronym for Distributed Data Over Multicast. And now let's introduce ourselves.
I'm Seth Pace.
Hi, my name is Rohan Haldia.
And I'm Jaden Bailey.
And my name is Jake Durham. At its simplest, our solution is a call system. Call systems in a network are typically controlled via a centralized server, as we've shown in this example. These servers will handle all the connections and connect each user to the person they intend to call. However, this approach has limitations in various high-stakes situations where you need to maintain communication without a single point of failure. Like, for example, what happens if the server goes down? Well, then all the calls would get disconnected and you wouldn't be able to have any sort of communication. To combat this, we've developed a distributed call management system that automatically meshes between users without the need for a centralized server using multicast. Multicast is managed by the router. And to explain how it kind of works, let's imagine computer one says, hey, I want to join this group. And what will happen is when another computer sends data to this group that's at the router will send it to all users in that group, which would be user one at that point. Additionally, more users can join this group, and so when that computer two sends data to this router, all users a part of the group will automatically receive that data. So now let's take a quick demonstration of our GUI. So starting off with this very front page, we have our join call, which allows us to set up a call. So I'm going to show off us joining a call. So we click on this and we type in the IP of the user that we want to connect to. And that'd be 0.6. So first user, I'll connect. You have an accept reject, and I'm going to accept. And by doing that, I set up this session with that user. So now I can then send a message to that user, and I'm also sending audio, which I'll play. It's not great in terms of as a demonstration for this video. So by sending a text, because we can do multimedia, you can see that I sent you to the other user. Now I'm going to add another user. So 22, I think, yeah. And by saying that, now we're in a three-way session with three users. And if I can send a message like, hello there, everyone. You can see it's sent to all of the users. Additionally, we are able to filter the messages. So like, let's say on this computer, I only want to see messages from port 14. I can filter that, and it's only port 14. If I go to the group, that's everyone, but at port 22 hasn't sent me any messages yet. Looking at our side panel, you can also set different devices that, like, for example, let's say I wanted to do a different microphone, or I wanted to play through, like, maybe not my speaker, my headphones. I can change that here. And we have IP history, which allows us to see the history of devices we connected to, which would be these two devices. Our solution uses many different components that can be abstracted down to this system diagram. At the left, or you can imagine the top, we have our GUI. This is what a user would interact with, and it would allow one to use our call system library that we have built. To interact with this library, we have the API calls that are accessed to carry out internal functionality. The data pipeline acts as our intermediary between our networking and I/O components. It also creates and parses all the packets that are sent out, including our session initiation and RTP, which is what contains data like text and audio. Networking is what sets up our TCP and multicast UDP sockets and provides an interface to access these. I/O handles our audio, which includes finding the microphone and speaker devices and setting up audio streams to get that microphone input and playback speaker output. Looking back, we could see how I/O, data, pipeline, and networking works together during a call. As, for example, in I/O, audio would be taken from the microphone. Then that audio would be compressed in data pipeline by one of our supported codecs, then be wrapped in an RTB header, creating an RTB packet. That packet would then be sent out in networking to all members of the user's multicast group. Our tech stack was carefully chosen to provide us with the best tools for our project. For the backend, we utilized the power of C and C++, which offered us granular control over system-level calls that were essential to the creation of our application. To complement this, we used the Uno platform for our front end, utilizing XAML and C# to design and create cross-platform applications. To interface with our C library and C# front end, we used the pinvoke libraries provided by .NET. For build automation, we relied on CMake, which allowed us to easily manage dependencies and cross-platform compilation. Additionally, we used Port Audio for cross-platform audio device APIs and Doxygen to create comprehensive API documentation. We also want to highlight that we developed from scratch our socket and networking library for TCP and multicast UDP, created the session initiation protocol and session initiation negotiation in accordance to specifications from the Internet Engineering Task Force, G711 codec support and pre-playback audio processing, and extensive error handling with automatic recovery from recoverable states. Some other important external technologies is our use of SpeedyLog for extensive and dynamic logging that is configurable based on the user's desired level of information and the standard modern codec Opus. Now, let's take a brief mention to some of the software engineering practices our team followed, starting off with the solid principles. These are a series of object-oriented principles our team took to heart while developing and designing this project. We also followed a strict separation of concerns, dividing up our project into 8 submodules that exist independently of one another for specific components of our project. Additionally, we wrote over 4,500 lines of code dedicated to verifying and validating each submodule to ensure project stability. We also took great care in regards to our week-to-week processes, setting up design channels for each submodule. We required mandatory code reviews before each merge request, and hold weekly stand-ups to maximize resource allocation. Thank you so much for listening, and we also want to give a special thanks to Scott and Marius from L3Harris for their help and time they spend every week with us.